Welcome, everyone. Let's get started. There are office hours right after class. Does anyone have any questions for now? Okay. Let's get started. So as a quick review from last time, we were looking at decision problems. So problems where there is a yes/no answer. And we looked at first the class P, which is the set of decision problems where the answers can be found in polynomial time in the size of the input. Then we looked at the class NP, where for every yes answer, there is some certificate that proves that the answer is indeed yes, and you can check that certificate in polynomial time. We looked at the class COMP, where for really no answer, there is a certificate that proves it is indeed no, and that can be checked in polynomial time. We say that a problem is polynomial time reducible to another problem if given answers to A, we can solve B in polynomial time. So if we had a magic solution generator for A, then we could use it to solve B in a quite short amount of time. And we say that a problem is NP complete if it's not just in NP, but if every problem in NP is polynomial time reducible to it. So in some sense, it is as hard as any problem in NP. And this is why NP complete problems are sort of seen to be the hard problems, at least out of the problems in NP. And then we saw that if B is an NP and A is NP complete, and if A is polynomial time reducible to B, then B is also NP complete. Are there any questions about any of this? Things that people didn't have quite clear from last time? Just what parts of this are confusing? Do we prove the second to last point? So the second to last point, we didn't prove that any particular problem is NP complete. It's somewhat difficult. It's something that we could prove if, we had a couple of classes to spend on it. Yes, absolutely. This isn't really a thing to prove, though, because it is a definition. But I think what you were meaning is, did we prove that any particular problem is NP complete? And we didn't. We proved that a problem was NP complete by reducing it to another NP complete problem. Or sorry, by reducing another NP complete problem to it. Sort of the intuition here is that by reducing a problem to another problem, you're saying that the problem that you're reducing it to is at least as hard as the first problem. Like, if I could, suppose I could solve world peace if only I could get a decent sandwich. Then in some sense, the problem of solving world peace the problem of finding a decent sandwich would be harder than the problem of solving world peace, or at least it would be as hard as that. So this question, we're taking a leap of faith that some well-known problem is NP complete, and to prove a new problem is NP complete, we use the last point. Yeah, I mean, I wouldn't call it exactly a leap of faith in the sense that we just don't have time to prove everything in this course, and there are some things that we've used which we haven't proven. But yeah. Unfortunately, it's not possible within the context of this course to literally prove everything from the ground up. We try to prove as much as we can given the time constraints, but so I hope that this gives you at least a sense that everything is provable from the ground up. Okay. So now let's look at one of the classic NP-complete problems, SAT, or satisfiability. So Boolean formulas are basically expressions like this. And you could read this as x1 or not x2 and x3. So how to read one of these formulas is each of these xi is a Boolean variable. It's either true or false. If you put a negative sign in front, that just means the negation of it. So if the original thing was true, now it's false. If the original thing was false, now it's true. The sort of v, which in LaTeX is written \v, \vee, is or. And this thing, this wedge, which in LaTeX is written \wedge, is and. That's just logical notation. So in this particular case, again, we have x1 or not x2 and x3. So in order for this thing to be true, you would have to evaluate each of these things as true. A Boolean satisfiability problem is the problem of working out whether a Boolean formula has any solutions. So in this case, there are actually a couple of solutions. One of the solutions would be setting the first variable equal to false, setting the second variable equal to false as well. So this would become true because it's not x2. So if x2 is false, then not x2 is true. So this whole clause evaluates as false or true, which is true. And then if we set x3 equal to true, then the second clause would also be true. So we need to have this thing be true and this thing be true. So one way to do it is to do false, false, true. So this evaluates as false or true and true. Questions? And if you're wondering about why this notation, it's sort of similar to set notation, where you can think of it as union. So this is like the union of situations where this is true and this and this is true. So either one of those is fine, but intersection is sort of reducing the possibility. So it's saying, look at the set of situations where this is true and this is true. You need an intersection of sets. So this is why there's sort of these two kinds of notation. You can think of this like set intersection and this like set union. If you aren't interested in that, don't worry. There's a question about the preceding slide. Are all algorithms in NP reducible to the same fundamental formula, or are there multiple unrelated fundamental problems? So an NP-complete problem, everything in NP is reducible to it. So for example, SAT, I'm about to say, SAT is an NP-complete problem. So anything is reducible to SAT, but then anything is also reducible to the traveling salesman problem, which we saw was NP-complete before. So you can think of NP-complete problems as all equivalently hard. There are algorithms which are in NP which aren't equivalently hard, but they are not the NP-complete ones. So for example, anything in P, remember, is also in NP. So it's not equivalently hard, it's strictly less hard. Is this used by logic programming? There's a question. So yeah, you can think of Boolean formulas as like really useful in logic. And so SAT is one of those problems that's sort of seen as a fundamental NP-complete problem, not in like, Again, any NP-complete problem reduces to any other, but SAT is something is very close to what you can prove is NP-complete. So there's a lot of you can think of sort of proving that one original thing was NP-complete, and then everything else follows from that. You can prove that since this is NP-complete, this must also be NP-complete. This must also be NP-complete. This must also be NP-complete. And there's like an original problem which was proven to be NP-complete, and that's sort of circuit complexity, but it's very similar to SAT. And it's because of this whole logic programming thing. Okay. So now we've seen just general Boolean satisfiability. We can look at a particular way of writing these formulae. So a Boolean formula in 3 conjunctive normal form, that's often abbreviated 3CNF form, has a series of clauses separated by AND, with each clause having 3 variables or in the negation separated by OR. So here, for example, we have the first clause being x1 or not x2 or x4. So that this first clause is satisfied if x1 is true, x2 is false, or x4 is true. This next clause will be satisfied if x2 were false, or if x3 were false, or if x4 were true. And then there's another clause here. And you can just keep on having as many clauses as you want, but each one has 3 variables or their negation. And those are all separated by ORs. So this is just a way of, it is a nice, consistent kind of formula. And in fact, any of the formulas that we were looking at on the previous slide, I realized we didn't see very many SAT formulae, but any SAT formula could be written in this form. And I won't show that, but it's pretty easy to show that if you rearrange it or you substitute more variables for some clauses, then you can end up in this nice form. So it's basically like in the same way that we sort of rearranged a linear program to get it into a form that enabled us to do something with it consistently. Here we can rearrange a SAT formula in order to get it into 3 conjunctive normal form, which is just enabling us to just predict sort of the structure of it. Like in a general form, you could have like ands in here, you could have lots of nested clauses, and that's just annoying to work with. Questions about this? So again, this standard form is sometimes more straightforward to work with. Now, 3SAT is the problem of determining whether a formula in 3 conjunctive normal form has any solutions. There's a question. Is this example just an example or the official form? This is just one example of a formula in 3 conjunctive normal form. The official form has to have a series of clauses. Within each clause, there are exactly 3 variables or their negation. And they are separated by OR, and the clauses are separated by AND. So you could have lots more clauses. You could have different variables in here. You could have different negations or not negations and so on. But in each one, there are 3. They're ORs, and between the clauses, there's AND. OK. Now, 3SAT is an NP-complete problem. Again, we're not going to prove this. But this is sort of the fundamental NP-complete problem for many people, or for many proofs. So it is, we could have showed, without too much work, we could have made this our primitive NP-complete problem. We could have proven that finding a Hamiltonian cycle is NP-complete using 3SAT, for example. OK. So now let's look at some more examples of NP-complete problems and why they're sort of related. Now, on the face of it, this graph theory is very different from 3SAT, but we'll see that actually there is a connection. A clique in a graph, if you remember from a long time ago, is a subset of the vertices where all the possible edges exist between them. So here's a 4-click, and here is a 3-click, colored in red, because all the possible edges exist here, and all the possible edges exist there. Given a graph G with n vertices, can we efficiently work out whether it contains a clique of size k? How would you go about it? If you were trying to find a clique of size k in a graph, how would you go about it? Yeah, are there any bad algorithms, or just like sort of the really simple algorithms that you might try? There's a good first cut, which is like checking, are there enough edges for a clique of size k? Because if you don't have n choose, if you don't have roughly k squared over 2 edges, then you couldn't have a clique of size k. That's a good point. So if you have enough edges, then if you don't have enough edges, that's a quick no. I'm assuming you do have enough edges. There's a suggestion to just brute force search. So this is in fact something you could do. If k is small, this is probably pretty doable. For example, if you're just looking for triangles, so 3 cliques, you could just check all possible n choose 3 groups of 3 vertices and see if they are all pairwise connected to see if there's a 3-click. Again, a 3-click is just a triangle. You could probably maybe do it for small graphs for k equals 4 too. But as k gets bigger, it gets harder. We can check these by brute force, but if it's polynomial time if k is a constant. So if you were just trying to find k clicks with k equals 10, say, then technically it's polynomial time. It's like n to the 10 time to check all of them, which is kind of bad, but it's still polynomial time. But if k were bigger than that, for example, if k were n over 2, then you got a problem. N choose n over 2 is exponential in n. So at least the naive sort of brute force algorithm is not going to be very good if k is large. So clique gk is defined as the problem of whether or not there is a clique in G of size k. Problem of finding whether or not there's a clique of size k. So let's prove that clique is NP complete by reduction from 3-sat. Again, 3-sat doesn't seem like it's related to graphs, but we can do it. What is the first step in proving that clique is NP complete? What's the easiest thing we can do? Remember, there are a couple of conditions for something to be NP complete. Yeah, we have to first show it's in NP. But that's pretty doable. If we want to show that it's an NP, we have to show there's a certificate which enables us to check quickly that that a yes answer is indeed a yes. So what's a certificate? Well, in general, if you have an NP problem, if you're trying to prove something's an NP and the problem is like find a thing, well, the certificate is generally just the thing that you're trying to find. Does this thing exist? Certificate, show me the thing. So click is in NP because there's a certificate, and the certificate could just be the click itself. If you showed me a k click, I could check that really fast, specifically in polynomial time, and I could assure myself that it is indeed a yes. So now we will show that 3sat reduces to click. And so this is the trickier part. And again, what this means is we need to show that if we could solve click, then we could solve 3sat. So typically the way that this sort of reduction process works is we take an instance of 3sat and we convert it to either one instance of click or several instances of click, and we say, okay, we could solve those click problems. That will enable us to solve the original 3sat problem. So let's see how this works. Suppose we have an instance of 3sat, so we're trying to solve this thing. This formula has clauses C1 through CK. And here's where it's useful that it's 3sat, because we know what these clauses look like. Each of those clauses, we don't know how many there are, but there's some clauses, and each of them has three variables or their negation in it. So let's define a graph with 3 vertices for every one of the clauses. And so what we're going to have is this graph looks like this. We have, again, 3 vertices for clause 1, 3 vertices for clause 2, 3 vertices for clause 3, and so on. And how are we going to connect them? Well, we're not going to connect anything in the same clause. These vertices are never connected. 2 vertices are connected if they are in different clauses, unless they are the same variable, like with one being the negation of the other. So for example, this is x1 and this is not x1. So we're not going to connect those two. And we'll see why we're doing this in a moment. But this one is not connected to this, but it is connected to this and this, because the only situation where things aren't connected is either if they're in the same clause or if they're in different clauses, but they represent the same variable in a negation. So x1 can be connected to x1, but it can't be connected to not x1. x2 can be connected to, not x2 can be connected to not x1, but it can't be connected to x2. Does this make sense? Are there any questions about how we're defining this graph? Don't worry about the colors in the graph. We'll see where that comes in a moment. Like I realize some are shaded more heavily than others. For a Boolean formula that's in 3 conjunctive normal form, can it have more than 3 variables, e.g. x4? Yes, absolutely. So this was just a small example. There might be x10 here. There might be a lot more variables, but this just happens to have 3 variables. So all of the clauses in this case have the same 3 variables, but you could have, like, this could be x10 here. More questions? So again, this is how we're defining this graph. We're taking a formula and we're using it to construct a graph. Now, we claim that finding a k-click in this graph is equivalent to finding a solution to the formula that we started with. And in this case, the formula, again, is this. Sorry, I rearranged the clauses a little bit. This is this clause, this is this clause, and this is this clause. Yeah, so why is that the case? Why does finding a k-click, here there are, in this case, remember, a k is the number of clauses, so here it would be a 3-click, so it would be finding a triangle in this graph. Why is finding a triangle in this graph equivalent to finding a solution? Well, first of all, a k-click has to have exactly 1 vertex from each clause. Now, why is that? Well, because we know there are no edges within a clause, because we defined it that way. So the only, in a k-clique, everything has to be connected. So you could never have two things from the same clause because we know they're not connected. So we can have at most one thing from every clause. But there are k clauses. So if it's a k-clique, it has to have exactly one from each of the clauses. That's the first thing. A k-clique has to have exactly one vertex from every clause. Next point. Any two vertices are unconnected between different clauses exactly when they're incompatible, if they're negations of each other. If they aren't incompatible, then they're connected. So x1 is not incompatible with x2 being true. There is no contradiction. If x1 and negative x1, those are incompatible. You can't have both of them be true at the same time. They're not connected. But any two things that are immediately compatible are connected. So if we assigned true to all the vertices in the clique, we would get a solution because there would be one true thing in each of the clauses, and no two of them would be incompatible. We wouldn't have assigned x2 and negative x2 both to be true. So we'd have a perfectly compatible solution, which gives us one thing, at least one thing true in each of the clauses. Vice versa, if we had a solution where we say, okay, well, this is the thing that's true here, this is the thing that's true here, and this is the thing that's true here, then we could pick out the corresponding vertices and say, okay, well, these three things form a triangle because no two of them are incompatible, and there is one in every one of the clauses. Questions? Again, what the point of this is to construct a graph where if we solve the problem of finding a clique, we have automatically solved the problem of finding a solution to the 3-sat formula. So we basically encode a 3-sat formula into a graph, and then if we find the clique, we've found a solution to the formula. And again, the steps here are we first define the graph. We say, okay, well, how is this graph constructed? We have 3 vertices for every clause, so one for every one of the variables or their negation. And then we connect two things if they're in two vertices if they're in different clauses, and if they don't have a contradiction, if they aren't the negation of the same variable. So any two things are connected unless it's like x1 and negative x1. And then we say k-cliques are literally equivalent to solutions to the formula, because if you have two vertices, because if you have a k-clique, then it has to have exactly one vertex from every clause, because if it had fewer than one, then there wouldn't be k, because there are k clauses. And if it had more than one in any clause, then those two couldn't be connected, because we said any two vertices in the same clause aren't connected. So it has to have a k-clique has to have exactly one in every clause. And if two vertices are connected, then that means that they are compatible. So we could set both of them equal to true, and we wouldn't have any contradictions in our solution. So overall, we can set all the vertices of a clique to true in order to get a solution, and vice versa. If we have a solution, then we can pick out the corresponding vertices in the graph, and that gives us a clique. What would you assign for k to pass to clique? The number of clauses. K is just the number of clauses in the formula. More questions, more things that are unclear. Yes, exactly, as was written in chat. What we need to do is to solve clique of this graph with k equal to the number of clauses in the formula. So it takes, therefore, answering this click of gk gives us an answer to 3SAT. And it takes just polynomial time to make this graph, g, which you have to build from the formula itself. Therefore, click is NP-complete because 3SAT is NP-complete. We showed that we can take a 3SAT instance and we can solve it if we could solve click. But since we know 3SAT's hard, that means that click has to be hard as well, because if we could solve click, we could solve 3SAT. Questions? Okay. Let's see another NP-complete problem. Given an undirected, unweighted graph G, a vertex cover of G is a set of vertices such that every edge of G has at least one of its endpoints in the set, possibly both endpoints. So we're basically trying to cover all the edges of the graph. We say, OK, well, each of those edges has to have at least one of its endpoints there. Here are some examples. The vertex covers are shown in red. So here, for example, we need to make sure that every edge in this graph has either one or both of its endpoints colored red. And here, indeed, this edge, for example, has one endpoint colored red. Here, this edge has both endpoints colored red. Here, again, it's a bipartite graph. And a bipartite graph, it's very easy. We can just color one entire side red. This is the Peterson graph, where here we can color these things red, and then every edge has at least one endpoint being red, and likewise with this funky graph. Another way of thinking about it is the set of vertices outside the vertex cover can't have any edges between them. So the black vertices here can't have any vertices between them, any edges between them, sorry. Because if there were an edge between two black vertices, it wouldn't be covered by the vertex cover. So that's just like is equivalent. Vertex cover is just whatever is everything outside the vertex cover has to be an independent set. That is another way to define the vertex cover. So we define the problem of vertex cover, gk, as the problem of determining whether G, some particular graph G, has a vertex cover with k vertices. Now, if we could have an efficient algorithm for solving this, we could apply it many times and work out the minimal vertex cover. We could just sort of gradually reduce k until we found the smallest size where G has a vertex cover. Like clearly G has a vertex cover with all the vertices. You just take all the vertices and you cover all the edges. Does it have a vertex cover with all but one of the vertices? Does it have a vertex cover with all but 10 of the vertices? Does it have a vertex cover with half or a third of the vertices? We could keep on decreasing k until we found out the minimal vertex cover. So that would be one way to work out the smallest possible vertex cover, just by applying this decision problem, vertex cover. Again, vertex cover is a yes-no problem, but we can use it to find a minimal size of a vertex cover. Let's prove that vertex cover is NP-complete. What's a good first step? Thinking back to what we did before. How can we start proving that something is NP complete? Show that it's an NP. First thing is showing it's an NP. So what's a good certificate? Is there a certificate that we could use? Suppose that the answer is yes, so there is a vertex cover of size k. What is a certificate we could use to check that the answer is indeed yes? Yeah, you just take the vertex cover itself. Like before, if we need to show that something exists, is it yes, no, does it exist, does it not exist? The thing itself is a certificate. You can easily check that a vertex cover of size k is indeed a vertex cover of size k. Somebody presented that to you as your certificate, you could easily check it. Okay. So it's in NP. Now what general strategy can we use? What might we do next? Let's find a reduction from something to it. You can find a polynomial time reduction from a problem we know is NP complete. So we have a few options now. Any thoughts on what we might want to reduce from? There are probably several ways to go about this, so there isn't one right answer here. So one suggestion was click. Let's try click. We want to show that we can solve click if we could solve vertex cover. So suppose we have to work out if a graph has a k-click. Again, we need to solve click. It's important to remember which way you're going here. We need to reduce click to vertex cover, not vertex cover to click. We already know that everything in NP reduces to click because click is NP complete. We need to show that click reduces to vertex cover. And again, just think about it logically. We know that click is hard. We need to show that vertex cover is harder, or at least as hard. So we need to show that if we could solve vertex cover, we could solve click, which is this hard problem. So we need to work out how to find a click, a k-click. We have a graph G, and we need to work out if it has a k-click. So what we're going to do here is we're going to take the complement graph. So the complement just means for every edge that was there before, now it's not an edge. And for everything that wasn't an edge before, now it is an edge. So for example, these two vertices were connected before. Now they're not. These two weren't connected before. Now they are. So this is every edge that wasn't here and no edges that were here. So that's just the complement graph. Right? Where this is the graph we're looking for. This is G. This is the complement of G, so H. Cool. So what can we do here? So let's think about clicks. We're going to try to find a click. We want to find a click in G. But what does it mean to find a click in G? Well, finding a click in G is the same as finding an independent set in H, because A clique is something where all of the edges possible are there. An independent set is something where none of the edges possible are there. So if this is a clique, for example, these 4 vertices form a clique. Now they form an independent set because we flipped edges and non-edges. So the complement, as it were, of a clique is an independent set, and vice versa. OK, so these 4 form a clique here. The same vertices form an independent set in H. How can we determine whether there is a K-clique? How can we link it to what we want to do? Remember, we're thinking about vertex covers. Any thoughts? Remember again, a vertex cover is a set of vertices where every edge has at least one of those vertices. It's a set of vertices that basically touches all the edges. So remember, we don't have to apply vertex cover to the original graph. We can apply vertex cover to any graph. In particular, we can run vertex cover on H, the complement graph. And we could run it to try to find an n minus k vertex cover, where n is the total number of vertices and k is the size of the clique we're trying to find in G. So what we're going to try to prove is that vertex cover of H n minus k is equal to clique G k. So if we run vertex cover on H with n minus k, trying to find a vertex cover of size n minus k, it's the same as whether there is a clique in G of size k. Let's see why that's the case. So if this thing is yes, we need to show that this is yes. So if vertex cover is yes, that's a vertex cover in H with n minus k vertices. For example, this and this form a vertex cover of H. This is our graph H. This is our graph G. This is a vertex cover of H because everything, all the edges, are connected to one of these two, possibly both. That means that everything that's not in the vertex cover is an independent set. Remember, this was another way that we thought about vertex covers. A vertex cover means that everything outside the vertex cover is not connected. There are no edges purely outside the vertex cover because every edge has to touch at least one of the vertices in the vertex cover. So if there's an n minus k size vertex cover, that means there's a k size independent set. Just all the vertices that weren't in there. Because n total vertices, n minus k in the vertex cover, k must be left over. Those must form an independent set. But since we're in H, we know that an independent set corresponds to a clique in G. So here is our vertex cover, 2 vertices. Here are the things that aren't the vertex cover, 4 vertices. Here are the same 4 vertices in G. And look, they're connected. They have to all be connected because there couldn't have been any edges here because this was an independent set because the other vertices formed a vertex cover. So that's one direction. If vertex cover is yes, then click is yes. There is a k-click in G. Now let's go the other way. Suppose vertex cover is no. There's no vertex cover in H with n minus k vertices. Could there be a k-click in G? Could we have this be equal to no, but this be equal to yes? Well, no. If there were a k-click in G, then it's just basically the same logic. If there were a k-click here, it would be a k-size independent set in H. And the other n minus k would be a vertex cover. So that means that we have a contradiction. There's no k-click in G. And so if vertex cover is a no, then click is a no. Questions about this? Again, what we saw is that we could solve vertex cover if we had access to this. We could solve click if we had access to vertex cover. But we don't apply vertex cover to the same graph. We apply it to the complement graph. If we can find a vertex cover of size n minus k, then everything else has to be an independent set. And if we have an independent set in H, then in the original graph, we have a click. Vice versa, if we have a click in the original graph, that corresponds to an independent set in the complement graph. And the independent set means that everything outside the independent set is a vertex cover. So it goes both ways. This is sort of like an if and only if proof. It goes both ways. It's because every statement is equivalent to every other. And then, now what does this all mean? Let's summarize the overall proof. We were trying to prove that vertex cover is NP complete. So to summarize, we first proved that vertex cover is in NP. Then we showed that we could solve click in polynomial time if we could solve vertex cover. And since click is NP complete, that means that vertex cover must also be NP complete. Oops. Questions? So hopefully now you've gotten a bit of a sense for how to show that things are NP complete. And this is not just, it's not just a sort of academic mathematical thing. Like, it is definitely useful to know when things are NP complete and to sort of have the concept of reduction in one's mind. If there are things in your mind that you know are hard, it's useful to see whether you should even be attempting a problem, because if you can reduce a hard problem to it, then that means that the thing you're trying is also really hard. And I've been in a situation where I've realized that something I'm trying to come up with an algorithm for is actually a really hard problem, like NP complete. In a formal proof, which problem could you assume that the reader knows is NP complete? So in the context of this course, you can assume that any of the things that we have shown are NP complete, or that we've stated are NP complete, are indeed. So any of the problems that we looked at, it's fair game, you can assume that they're NP complete. Now, if you were writing a paper, you could just cite that any particular problem is NP complete if there's already a proof of it. All of these things, you wouldn't even need a citation probably, because they're sufficiently well known. But I would just say, the problem of finding this is NP complete. Are there competitions for the weirdest, most complicated NP problem someone can reduce a given problem to? Yeah, Well, I mean, maybe not competitions, but I know there is this entire area of sort of playing around with cool problems. Yeah, like someone is posting in the chat, Donkey Kong is NP hard. You can prove that a lot of games are NP hard with certain assumptions. You need to turn them into decision problems. And this is basically like in the context of these various games, like I seem to remember like Minecraft for some definition of like, you have to turn Minecraft into a decision problem. I don't actually play Minecraft, so I wouldn't be the one to describe this, but as I understand it, in Minecraft, there are like certain things that you are building. And if you are trying to do a reduction from something, you can basically encode an instance of something like 3sat into Minecraft and show that if you could solve Minecraft in some sense, then you could solve 3sat. I don't know if it was from 3sat, but it's something like that. So we are now at office hours. I'm happy to stick around for more questions. In the meantime, here is a poll about the speed of class. And I look forward to seeing everybody next time. We will talk about approximation algorithms. So when the NP hard problems aren't actually as hard if you're prepared to relax them a little bit.